Hello everyone. Today we are presenting digital twins and mHealth design guidelines for upper limb rehabilitation. This work was produced by Guadir, Omar Hernandez, Edna, and Ramiro Plazas, members of the Industrial Control Research Group (GISI) at the Universidad del Valle. This is our outline. This slide introduces the practical application of digital twin integration as a key to map out the intricate neuromechanical deficit caused by physical impairments. It is essential to synthesize disparate data streams captured across distinct physical and physiological scales. By executing a hybrid multimodal data fusion that links contextual mobile telemetry with high-fidelity laboratory metrics, we can construct highly individualized virtual representation of the human musculoskeletal apparatus. This framework continuously contextualizes clinical profiles through a continuous ecological gait assessment conducted directly within the user's daily environment. Driven by this active synchronization, the digital counterpart shifts medical protocols toward automated precision. It generates a predictive patient-specific prognosis, triggers proactive neuromuscular injury mitigation before mechanical failures manifest, and governs cellular therapeutic pathways under a system of ubiquitous closed-loop rehabilitation. To begin, this slide illustrates why we need a technological shift in healthcare. The World Health Organization, through its Rehabilitation 2030 initiative, demands new solutions to warranty, continuous, and high-quality care. On the left side, we see the limitation of conventional rehabilitation. Today, assessment depends too much on subjective observation, making it hard to detect small, incorrect movements. Traditional tools also create high variability in data, and patients face strict access barrier because therapy is restricted to hospitals. To solve these problems, our work introduces the high fidelity digital ecosystem shown on the right. By using advanced wearable sensors, we change discrete clinical observation into continuous multimodal data streams. This allows us to capture complex human movement and physiological data in real time. With advanced algorithms, we achieve objective and accurate tracking of safe joint movements. Ultimately, this technology enables true decentralized telerehabilitation. We successfully move care directly to the patient's home, closing the gap between clinical goals and real patient recovery. These slides present the core technical methodology of our work, focusing on the convergence between physical and digital environments. Our objective is to unify portable instrumentation with advanced biomechanical modeling through a structured computational framework. On the left, we have the physical domain represented by record. This is our sensing layer. It utilizes a low-cost mHealth platform and advances wearable technology to capture movement data. This study is entirely focused, focused on the patient's interaction and data acquisition in non-structured everyday environments. On the right, we have the digital domain represented by twin axis. This is where the digital twin resides. Here we apply 2D kinematic models to transform raw telemetry into a virtual representation. This allows for the systematic validation of joint rings with clinical precision. The most important element is the objective computational break in the center. This is the engine that enables bidirectional synchronization. It provides real-time clinical feedback and ensures that telerehabilitation is not only accessible but also medically secure and standardized by integrating these three components. We create a reliable system that translates wearable sensors data into actionable biomechanical evidence. This allows for precise monitoring and effective rehabilitation directly in the patient's home without sacrificing clinical rigor. This graph shows the main hypotheses of our digital twin frameworks for mHealth applications. At the top, we propose isolating the sagittal plane by tracking only shoulder and above flexions. We minimize the computational load. This optimization will allow our digital twin algorithm to run smoothly on low power wearable sensors. The main area simulates how the model monitors biological balance. The green line is the predicted muscle load. The red dashed line represents the hypothetical tissue tolerance threshold, which decreases due to fatigue. Our model captures two biomechanical phases. Peak 1 is the active flexion with maximum strain, and peak 2 is the controller extensions. The most important part of our hypothesis is the red circles. They represent the critical zones. Our goal is to predict when the muscle load crosses the tolerance threshold. When this happens, the future mHealth app will send a real-time feedback alert to prevent injuries during home rehabilitation.
Hierarchical cyber-physical architecture. These diagrams show how the physical patient and the digital model work together in a closed loop. The blue border represents the NASEM guidelines, is the outer rule protecting medical safety and standards throughout the whole project. On the left, the physical domain, the real patient performing shoulder and elbow exercises tracked by wearable AMU sensors. This captures real data, but also noise and errors we need to fix. At the center, the embedded BBQ engine, the heart of our engineering work, it verifies the code, validates movement against real human limits, and quantifies sensor errors. On the right, the virtual representation and human-in-the-loop deployment, the verified data feeds the digital twin, letting the system predict risks, optimize treatment, and prevent injuries. mHealth platform, MVC architecture, and portability. This slide shows our mobile apps structure, built on a model view controller or MVC architecture, three independent layers working together around the user's phone. The controller is the background engine. It receives raw AMU signals and applies filters and fusion algorithms to clean and synchronize the data. The view is the Android interface. It animates the digital twin in real time and shows visual alerts if the patient makes a dangerous movement. The model handles clinical traceability. It uploads essential metrics to a secure cloud database so doctors can review history and track recovery remotely. Signal decoding funnel. This slide presents our decoding funnel, how we turn raw, noisy, wearable signal into meaningful clinical information in three stages. Input. raw inertial data from the accelerometer, gyroscope, and magnetometer calibrated specifically for upper limb rehab. But these raw signals suffer from artifacts, drive, and magnetic distortion. Process. Our processing curve filters environmental noise, solves inverse kinematics for joint angles, and applies biomechanical correlation to clean the signal. Output high-value clinical indicators. Data displayed these as validate functional scales, like the Fugue-Meyer assessment and the Action Research Arm test. This funnel bridges raw hardware telemetry and real clinical tracking, letting physicians evaluate recovery accurately and remotely. Clinical impact, biofeedback, and patient adherence. Our framework works as an intelligent closed-loop tele-rehabilitation system built around the intelligent closed-loop curve with three objectives. First, the biofeedback system is shows hidden joint angles to the patient in real time, simulating neuroplasticity and accelerating motor learning at home. Second, safety and injury prevention. Predictive algorithms detect muscle fatigue or dangerous movements and trigger alerts to stop the session automatically. Tier, gamification and engagement. Progress becomes gamified elements, reducing throughput and boosting long-term adherence. These three modules turn a simple wearable sensor into a safe, engaging, and clinically effective therapeutic loop. In conclusion, modern upper limb rehabilitation needs patient-centered, high-fidelity digital ecosystems. But our field lacks structured frameworks to translate clinical needs into precise software, which limits clinical adoption and rigor. Our work addresses this gap with clear design guidelines. Here's our roadmap: Phase 1, wearable sensor capture, an mHealth framework with low-code sensor nodes. Phase 2, dynamic representation, and adaptive digital twin for continuous predictive simulation. Phase 3, mass deployment and validation, a cloud-based BBUQ infrastructure for secure multi-patient tracking at clinical scale. This led to our goal: a standardized clinical decision support system driven by deterministic metrics, ensuring long-term therapeutic equity for every patient. This roadmap bridges clinical needs and software design with both fidelity and scientific rigor. Thank you for your attention. I'm open to any question you may have.